Hello everyone. Today we are looking at the quantification of XPS data and how we take into account that thing that everyone knows is all over any surface you might want to put into an XPS carbon overlayers. Okay, we have to acknowledge the universal truth of XPS analysis. If your samples have been loaded from atmosphere, been in your lab, sitting around, or worse, you've touched them with your fingers for some reason, you're going to have carbon on your surface. Yes, this can be a pain, but this can also be a useful way to energy reference if you've got insulating samples. So it's a bit of a blessing and a curse. An XPS is, of course, a surface sensitive technique. So if we stick carbon on our surface, we're going to see carbon. So as a quick recap, this is due to the way that electrons travel through solids, and that is to say, badly. They are very easily scattered by matter, and this is why we have to do our measurements in vacuum conditions, or the atmospheric gases would stop any of our photoelectrons from ever reaching the detector. The distance between successive collisions is known as the inelastic mean free path, and this is a property dependent on the material composition and the kinetic energy of the outgoing photoelectron. It is this value that gives us our information depth. But you might have picked up on something I said there. This value depends on the kinetic energy of the photoelectron. That means it's not the same for different parts of our spectrum. And that means our information depth is dependent on the binding energy. If we have, for example, a nickel metal foil with a small carbon overlayer, our nickel 2s photoelectrons have an information depth of around 5 nanometers, but our 3s electrons have an information depth of 11 nanometers. Now, XPS quantification basically assumes one thing, that your sample is homogeneous. Now, there are methods that we can account for this, one of which we are discussing here, but this is the base assumption. If you have a heterogeneous sample and you're trying to quantify two peaks that are quite far apart, clearly you're not going to be getting equal weighting of the two photo emissions, so your quantifications are not going to be accurate. To make things worse, this adventitious carbon level isn't even consistent between relatively similar samples. Recently we were looking at some high surface area titanosilicates with slightly different surface acidities, and the thickness of this carbon overlayer doubled from our low acid site concentration to high. And if we look at different classes of materials, we're going to get even bigger differences in this adventitious layer. So it's not even like we can apply a consistent algorithm to all samples and to all spectra. Now, there have been quite a few approaches in the literature to address this. However, an approximation approach from Graham Smith is probably the simplest approach and is the one we're going to look at here. All we need to know for this is the concentration of our carbon, which we can get from our initial quantification, and the effective attenuation length of the photoelectrons through our carbon layer for each peak, including the carbon 1s, which we can calculate relatively easily using a number of different methods and widely available softwares. If we know the effective attenuation length for the C1s photoelectrons through a C1s hydrocarbon layer, we can estimate the carbon thickness using the above equation. Now, for the majority of cases, you're going to be doing XPS perpendicular to the surface normal. So here, cos theta is going to cancel out as it equals 1. So now if we have a thickness, even if it's just a rough approximation, we can start to work out how our other peaks might behave through that thickness of carbon overlayer. Because of course now we can just use a Beer-Lambert style attenuation equation where in this case we know our corrected or attenuated intensity, we know our path length roughly, and we know our proportionality constant, which is in this case is going to be the effective attenuation length for the photo emission of interest. So if we have all of these, we can work backwards and calculate our I0 signal. So let's just take a look at this in action. We've got one of these titanium silicates that we quantified and found that we had 6.1% of carbon on the surface. If we take our calculated effective attenuation length, we can put our carbon intensity into our equation. So we have 1 minus 6.1 over 100. We then take the natural log, we multiply this by the negative of the C1s effective attenuation length, and then bam, we have our thickness, which in this case is around 0.2 nanometers. Now this is our path length that we can take into our next equation. We can then use the calculated effective attenuation lengths for our titanium 2p, our silicon 2p, and our oxygen 1s through a hydrocarbon layer, and calculate what the atomic percentages would be if the carbon layer did not exist. Now, of course, these are going to be above 100 because we should be increasing our signal. So we then need to renormalize these back to 100, and we have our final quantification. So that's it. It's a really nice and simple method to correct your data for carbon overlayers. Now, it should be said, this model does use a few assumptions, namely that all of your carbon is adventitious. So it's great if you're working on things like oxides, no good if you're working on carbon-based materials, sorry. It also assumes a flat and continuous coverage of carbon and no interaction with the sample itself. Now, this may or may not be true for your samples, but it does give you a very useful and quick method to correct your data if it is suitable. And if it isn't, well, hopefully it gets you thinking about what correction methods might be suitable to apply for your particular system. Anyway, that's all from me today. I hope you found this useful, and we will be back soon with some more XPS videos. Thanks for watching, and I'll see you soon. Goodbye.